To finish things off today, let's revisit the relationship between energy and equilibrium in the context of acid-base reactions. So particularly in the context of acid-base equilibria like this. How does anionic charge stability figure into the direction of acid-base equilibria? Well, it's this key idea that the downhill side of the reaction is favored. So stabilizing, for instance, an anion will tend to make that anion less basic. Decreasing its stability or increasing its energy will tend to make it more basic. So to give you a hypothetical scenario, let's imagine the theoretical scenario where the anion is exactly the same stability as the neutral compound. In this case, the anion and the neutral compound would exist in a 1-to-1 ratio. As we stabilize the anion, we tend to encourage its formation because we're making the reaction exothermic and favorable. This also may have the effect of lowering the activation energy, although that's not certain. Similarly, if we raise the energy of A-, we destabilize the base, send it back towards the conjugate acid form, and favor that conjugate acid form. These same rules apply if you're looking at a conjugate acid-base equilibrium and not just dissociation. So to look at an equilibrium, let's take a theoretical HA plus B minus goes to A minus plus HB, and really ignoring the neutral species, we can place simply A minus and B minus on this graph and think about how the equilibrium between these two will favor the lower energy species. So in this particular case, B minus would be favored, and we would actually favor the reverse rather than the forward reaction. Determining the relative stability of anions comes down to thinking about the three factors we've just looked at. That's why it's important to understand the factors that control charge stability. As sort of a teaser for next time, here are the three factors that control the charge stability of cations. Two of them should look very familiar to you. Delocalization and hybridization make a return as stabilizing factors for cations, but the third factor is a concept called hyperconjugation that you may not have seen before. So we'll look at hyperconjugation in great detail. The nice thing about hyperconjugation is that it's easy to understand in terms of orbital interactions. So if you've been keeping up with orbital interactions and really understand their origin and their nature and their potential for stabilization, then you should catch on to hyperconjugation very, very quickly. And hyperconjugation really boils down to a substitution effect in terms of stability, and the observation that more substituted carbocations tend to be more stable. The thing to keep in mind in the context of cations is that stable cations are weak acids. They don't want to give up protons because they're stable with the positive charge, and so to give up H+ would maybe potentially destabilize them. They're bad at letting go of positively charged protons. So a couple of thoughts for next time. How might cation stability figure into acid-base equilibria? Try to think of a few examples of your own, or come up with a few examples maybe from your own textbook in which cation stability is important for an acid-base equilibrium. And then of course, how do the factors that we've already talked about control the stability of cations? How do they work in terms of fundamental organic chemistry? These are questions we'll visit next time. But for now, that's all I've got for you. Thanks for joining us today, and I'll see you next time.